All right, this is the intermediate form of a diprotic acid. We're going to solve for all species. So I picked a system of aminophenol, 0.1 molar, and I looked up the Kas. Ka1 is 2 times 10 to the minus 5th. K2 is 1.05 times 10 to the minus 10th. And I went over here and did a Kb2 calculation because I know I'm going to need it. It's 5 times 10 to the minus 10th. So the question, that's our setup. The question becomes, what happens when we throw 0.1 molar KHA in solution? Well, that's easy. We get KHA plus water, or single arrow goes to K plus HA minus. It's a soluble salt, goes 100%. And here comes our problem. HA minus then goes on to react with water to give us two products. Let's do A minus 2 plus H3O plus, and that'll be Ka2. And we can have HA minus plus H2O can also act as a base, and that gives us H2A plus OH minus, and that gives us Kb2. So Kb2 is 5 times 10 to the minus 10th, and Ka1 is 1.05 times 10 to the minus 10th. I made a mistake up here, and you can look this up. Ka2 is 1.05, and no, I got it right. 1.05 times 10 to the minus 10th. That's right. Okay, so with that situation, I got problems here. Because this is a weak acid, it doesn't go very much in either reaction, but both of them produce, one produces H3O plus and one produces OH minus, and these two can go on and react, which is going to remove them from that side, which is going to shift both of them that way. Le Chatelier's principle. So that becomes hard to do. Now, on page 216 of your book, they solve systematic equations, and it's complicated. You might want to look into this, and it's interesting, but most of you will not care. Okay, so we're going to go right to the end point of the solution, and that is, I'm going to leave those KBs up here so I can see them. That is that the square root, or the concentration of H plus, is equal to the square root of Ka1 times Ka2. The book calls them K1 and K2 times concentration of HA minus plus K1 times the concentration, or Kw, divided by Ka1. This should be Ka1 up here. I'm going to drop the A's on them, plus the concentration of HA minus. Now, this is complicated. Number one, we don't know what this is. We know our initial concentration, which I didn't write down, so we'll pick one right now. We're going to dump in, I did pick one, 0.1 molar aminophenol right up here. So we're going to dump that in. That's called the formal concentration. The formal concentration of HA minus is 0.1. This is really the mass balance. It's equal to the concentration of HA minus plus the concentration of H2A plus the concentration of A minus 2. All the forms of A. And that's 0.1. Since this doesn't dissociate much up here, either reaction, I can say that the concentration of HA minus is pretty much going to be equal to the formal concentration of HA minus, which is equal to 0.1. It doesn't change, okay? So I'm going to plug that value in, the concentration of H plus is equal to the square root of Ka1 Ka2 times formal concentration of Ha minus plus Ka1 Kw divided by Ka1 plus the concentration of Ha minus. Now I got my assumptions, and here's where you have to be a little bit leery. Assumption number one, actually two. Assumption number one was the concentration of Ha minus is equal to the formal concentration of Ha minus, KHA in this case. Okay. Number two is going to be that if I look at the bottom of this, Ka1 is typically a small number, so the formal concentration of Ha minus, which is 0.1, maybe 0.01, is typically very much greater than Ka1, which implies at the bottom up here, Ka1 plus the formal concentration of Ha minus is going to be equal to the formal concentration of Ha minus. I made a mistake. This should be the formal concentration of Ha minus. Number three, third assumption is going to be on the top part up here. We're going to say that Ka1, and I got a Ka1 over here, and a Ka2, and a Kw. Notice that Ka2 is almost always bigger than Kw. And the formal concentration times the formal concentration is going to be larger. These two are typically much larger than Kw. That means my top becomes Ka1 times Ka2 times the formal concentration of Ha minus. With those assumptions, this becomes real nice. The concentration of H plus, change to black, the concentration of H plus is equal to the square root of Ka1, Ka2 times the formal concentration of Ha minus divided by formal concentration of Ha minus. These cancel, and I get the square root of Ka1 and Ka2. This is almost always true. This is true for us all the time. When it's going to fall apart is when my concentration, the formal concentration, gets really small. It's clearly going to fall apart. Or if Ka2 is pretty large, or Kb2 is, either one of them get large, it's going to be a problem. Okay? Because too much dissociation is going to occur. So, it might happen once in a while, and you'll be able to tell when it does, because your main assumption right up here is not going to work. That's where it'll fall apart. Alright, so what's this mean? We can solve for the concentration of H plus. I'm going to do one other thing. pH is equal to the negative log of H plus, which will be equal to the negative log of square root, well, let's write this way, Ka1 times Ka2 to the 1/2 power, which is equal 1/2 pKa1 plus pKa2. A very, very useful equation. This is where you're going to be all the time. Okay? So, on the exam, you'll be given this equation here, and I'll expect you to know which one of these are true. The only one that we're really stuck with is this one, this first assumption. Yeah, my coloring is not working. The first assumption here is the one we're going to be stuck with, okay? We can't do anything about it. There we go. Red. Red on red. That's our assumption that we're going to be stuck with. If that one doesn't work, you have to do successive approximations, and we're not going to do with it. So let's calculate all the concentrations of all our species now. Okay, let's continue on. Since I know H plus, okay, then I know that my HA is come on, HA minus is 0.1. Then I can solve for H2A. So I can do these two equations. Ka1 is equal to the concentration, actually sorry, I got confused. Ka1 is equal to the concentration of HA minus times the concentration of H3O plus divided by concentration H2A. We know this, we know this, we know this, okay? And so I get Ka1, which is, I forgot, where'd it go? 2 times 10 to the minus 5th is equal to 0.1 times the concentration H3O plus, which is 4.517 times 10 to the minus 8th divided by the concentration H2A. And so when I do that, I get the concentration of H2A equal 4.517 times 10 to the minus 8 times 0.1 is 10 to the minus 9 divided by 2, exponent change sign 5, and I get 2.25 times 10 to the minus 4th. And I can do the same thing for Ka2. Ka2 is equal to the concentration of A minus 2 times the concentration of H3O plus divided by HA minus, and so that should give me 2.25 times 10 to the minus 4th. I can get from Ka2 right here, I can get A minus 2 times concentration H3O plus, gives us HA minus, plug my values in, and I get A equal 2.32 times 10 to the minus 4th. Okay, if we look at these numbers, if I can scroll a little bit, we notice that the A minus 2 is bigger than the H2A, so if I go up and look at my K's, KB2 is in fact producing H2A, and it's a little bit bigger than Ka2, which is what we expect. Alright, so that's how you solve for all those. It's really this last part that you have to worry about, starting right here on these. Okay? Good enough. We'll talk about it in class.